So one of the approaches that is suggested is, well, look, let's use what's called an OBLA. Now this was in your definitions list. So again, OBLA is a protocol that's been devised to identify lactate turn point. And the notion of this, and I know some of you may have come across OBLA when you've done BTEC or A-level studies, is that the OBLA was where we would use a fixed lactate concentration. So this isn't about looking for the kick, it's about looking for the workload where we get a fixed concentration of 4 millimoles. So first proposed by Maeder back in 1980. And so this really almost does predate the work by Yeh. There was obviously concerns up to that point, but the notion is, look, it's really difficult to identify this visually. It's really difficult to identify where this transition is. Quite clearly in that zone that Benneker put forward in that schematic earlier, which is the maximal lactate steady state zone, and could have been anywhere in that zone. Their argument is, well, look, if you use a 4 millimole concentration, actually, that seems to tie in pretty closely to most other studies. Most studies seem to find if you do it visually, it's about 4 millimoles. So just use a fixed concentration. Well, the argument was this: well, if you look at the majority of studies, the majority of studies and data sets will show that the lactate response to exercise intensity would appear to be fairly linear up to about a lactate concentration of 4 millimoles. And beyond 4 millimoles, guess what? It starts to drift away. So the argument is 4 millimoles is that lactate turn point, the LT2, therefore it's your surrogate measure of maximal lactate steady state. And in fact, when they reported this, and this wasn't just reported by Maeder, it's been reported by subsequent studies, when you look at a range of abilities, different sporting background, and you look at lactate turn point, what they found was not 4 millimole, just lactate turn point using other methods, visually or whatever. It was associated with the lactate concentration of between around about 3.4 to 4.8 millimoles. Average is 4 millimoles. So there is some logic to what Maeder is proposing. Here you can see it. This is a study by Ghosh in the Malaysian Journal of Medical Sciences. But can you see we've got the speed, it's kilometers an hour, so it's a decent athlete. You look at the data points, and it'd be pretty difficult using the data points to visually identify the lactate turn point, right? I mean, you could take a guess, and you might go with 23 or 24. But what they've said is you use the fixed lactate concentration, 4 millimoles, that's the point. And the logic is that, if you're looking particularly in a clinical population group and you bring somebody back, you always look for a fixed concentration because you're interested in whether the exercise intensity for that fixed concentration has changed. There are huge problems with this though. The implication is that everybody gets to turn point with a concentration of 4 millimoles. Yet it's acknowledged that it's a range of 3.4 to 4.8. Okay, that's a 1.4. Is that right? Have I got that right? It's a 1.4 millimole bridge. It's a big difference between 3.4 and 4.8 millimoles. That's an enormous range over which it could be. So not everybody's 4 millimole. It's implying that everybody has this at the same lactate concentration. And yet we know, for example, in world-class athletes, as you see here, these are 800 metre runners, but world-class athletes, their maximal lactate concentration at VO2 max is 4 millimoles. So there's no way it's going to be 4 millimoles at lactate turn point. So there's no way the surrogate indication of maximal lactate steady state is going to be 4 millimoles. Yes, there is some evidence to suggest on average it's 4 millimoles. But we're scientists. How can we assume that everybody fits this? Secondly, if we go back to this data from Carter and Jones, look what happens following training. The lactate concentration falls. You couldn't identify that using a fixed concentration because the concentration is fixed. It's also worth noting that in this example here, look at the lactate concentration. Post-training, it's at 1 millimole. Pre-training, it's well, what we're looking at there, about 1.5 millimoles maybe. Certainly not a 4 millimole lactate concentration. So we really have to question the utility of using a fixed concentration. In fact, there's a number of protocols that exist for using this, particularly for identifying lactate threshold LT1. Use a fixed concentration. But everybody's different. So how can we propose to use fixed blood lactate concentrations? They don't allow us to identify change, and they also imply that everybody physiologically is the same. So use them with caution. But that still doesn't clear up the issue that we've got in terms of visual inspection is not the best approach to use. So what other methods have we got?